Hello everybody and welcome back to another video by Funlearn Tutorials. In today's video we will talk about certain properties of a relation, and we will in the future video discuss what are the names of those particular relations where certain properties hold. Now just a quick recap of what a relation is. A relation essentially is, as the name suggests, a relation between two or more elements of a particular set. So what are the 5 properties that we will be talking about? So the first property is called the property of reflexivity. So what do you think when you hear the term reflex? So when we want to do something and we take an action on ourselves without thinking too much, that is a reflex, right? When we touch fire and we react immediately, we do not think that we need to remove our hand from that fire in order to prevent ourselves from burning. We just do it. We just do it without thinking. So that's reflex, right? Now where does this reflexivity come from? Reflexivity essentially is a property that deals with an element of itself. So we will be talking about that particular element itself. We will be discussing more about it when we exactly find out what mathematically the property of reflexivity is. The next property that we will be talking about is the property of transitivity. So the property of transitivity. Again, if you have heard the term transitive before, it's basically a connection between 3 elements. So you take 2 elements and you establish a connection or a relation between them, and you take another third element with the second element and you establish a connection with the second and the third element. Then you assess whether a relationship between the first and the third element holds or not. So that is the relationship or the property of transitivity in a relation, and that again we will be talking about when we move into details of the property of transitivity. The third property is the property of antisymmetry. So the property of antisymmetry again is a little bit difficult to explain in pictographic ways, so we will be discussing it when we talk about the property of antisymmetry in mathematical terms. Then we have something called the symmetry property. Again, antisymmetry property and symmetry property, when we start looking at them, we realize that they start with the same concept in mind, but the conclusions derived are different for these 2 properties. So one is symmetry and the other property is antisymmetry. The fifth and the final property that we will be talking about is the property of completeness. In simple terms, the property of completeness deals with whether we can comprehend the entire set or not. So now that we have the 5 properties that we will be talking about, let us now look at one property at a time. So let us say that we have a relation R, right? We have a relation R, and what it essentially means is, suppose R may be the relationship is greater than. So we are talking about the relationship is greater than. Now what do we mean by R is the relationship is greater than? Suppose we take the set of natural numbers. Natural numbers was the first set of numbers to be discovered, because it's essentially the set of countable numbers. Natural numbers means the set of countable numbers. 1, 2, 3, 4. Sometimes in some books the set of natural numbers is also called positive integers. Why are they called the positive integers? Because we actually have sort of 3 types of integers. We have positive integers, and we have negative integers, and we also have 0, which is an integer but is neither positive nor negative. 0 is an integer which is neither negative nor positive. So we have 3 integers, sets of integers essentially. We have the negative integers, 0 which is neither positive nor negative, and we have the positive set of integers. So if we consider the positive set of integers, it's actually 1, 2, 3, which is the same as the set of natural numbers. So let's start with the set of natural numbers because it's the easiest to comprehend. Let me change my pen color to a little different color. So now we will be talking about relationship as is greater than, and we will be looking at elements from the set of natural numbers. Now what do I mean by a relation in this case? Let us look at one particular, or maybe let me say that this relationship will be greater than equal to. So let us take the relationship is greater than equal to. Now what do I mean by that? Let's say I take a number 3 and I take the number 5. So 3 is a natural number or a positive integer. and 5 is also a natural number or a positive integer. Now if I take 3 and I take 5, and if I put the relationship like this, is this true? Is 3 greater than or equal to 5? The answer is no. 3 is not greater than or equal to 5. So in this case, if I take 3 and 5, the relationship does not hold. But if I take the number 5 and I take the number 3, does the relationship now hold? Of course it holds. 5 is greater than 3. So if I take the number 5 before the number 3, then the relationship will hold. Note that the order is of importance here. If I take 3 is not greater than equal to 5, but 5 is greater than equal to 3. So in this case, we say that the relationship holds. Let us take a third example. Let's say I take 3 and I take again the number 3. There is no condition where it says that I cannot take one number twice or more than twice. I can take the same number more than once. So I can take 3 and 3 and I can try to establish a relationship between them. So now does this symbol hold? Now can I say 3 is greater than equal to 3? Again, I can, because in the previous relationship 5 was greater than 3. So if I look at the sign, it was 5 is greater than 3. So this part of the symbol was holding. So it's 5 greater than 3. But since it's part of greater than equal to sign, of course this entire bigger expression also holds. Now if I look at 3 greater than equal to 3, 3 is equal to 3. So this part holds. So it's again a true relationship. So I can say that 3 is greater than equal to 3. So this holds again. Now let us look at the relationships, the properties of the relationship. So this was just a discussion of what I mean by a relationship. So now we will be talking about one relationship at a time. So let us change the color to reflexivity to red, and I'll be talking about reflexivity. So what was reflexivity all about? Essentially, as I said, reflexivity deals with the particular element itself. As you see before, initially I was taking two numbers. So I took 3 and 5, I took 5 and 3, I can take any other number. But when I say reflexivity, it's an action that I do on my own self, right? When I see a fire, I move my hand away from it. I do not think about it, but I'm doing it spontaneously. I'm doing it by my own self, right? So reflexivity is similar. What do I say? আমি ওই জন্য রাত্রিবেলা করার চেষ্টা করি. So let me take, let's say for example, let me take the number 7. So if I take the number 7, since it's the property of reflexivity, I have to use the number 7 itself. I cannot establish a relationship between 7 and say 9 or 7 and 12. I have to work with 7 itself. So what do I say? What is the property of reflexivity? The property of reflexivity says, let me mention the mathematical expression, then we'll look at it in terms of an example, and then we'll see what we actually mean by the mathematical example. So let me just say the mathematical expression. The property of reflexivity says that for any x belonging to the set of numbers that you have chosen, so actually let me include something before that. Let me say for all x, small x. So for all small x, which represents the element belonging to the set capital X, which is the capital X set of numbers. So small x is an element, capital X is a set of numbers. For all elements belonging to a particular set, small x, relation small x. So whatever relationship that is, when I put that relationship on that element itself, that element, this x and this x are the same. X holds. So for all elements small x belonging to capital X, small x, capital R, small x, means small x related to small x holds, then we say that the property of reflexivity is satisfied. Now what do I mean by that? Let me take any number. Let me take the number 7 as I mentioned. So 7 belongs to the set of real numbers. So I took a number 7. Now I say that I want to compare, and let's say for sake of simplicity, I take the relationship to be greater than equal to. So in this case, my small x is 7. So small x equal to 7 and capital R is greater than equal to. So I am taking small x equal to 7 and capital R is greater than equal to. Now I try to look at this relationship. So I try to look at this relationship and I say, so in place of x I put 7, in place of R I put greater than equal to, again in place of x I put 7. Then I see whether this holds or not. Is 7 greater than equal to 7? Is 7 greater than equal to 7? The answer is yes. 7 is equal to 7. Naturally 7 will be greater than equal to 7 as well. So 7 greater than equal to 7 does hold. In that case, I say that the reflexivity property holds. This is just an example. Now we need to prove it generally. What do? We say, let me take any number small x. Let me take any number small x. If I say for any number that x will be equal to x, the same number, I am not talking about just a general number, I am talking about a specific small x from the set of, let's say the set of this capital, for the previous example this capital X was n. So okay, let me do it in terms of a question. So let's say I have been asked, let me write a question and let me answer it for you so that you can understand what I'm talking about. So let me say, test for the property of reflexivity for the relationship greater than or equal to, so for the relationship greater than or equal to on the set of natural numbers. So we are going to test for the property of the relationship, property of reflexivity for the relationship greater than equal to on the set of natural numbers. So in this case, what are we given? We are given that R, the relationship, is greater than equal to, and we are given capital X, which is the set of numbers that we will be considering. So it's actually this capital X. We have been asked by the question to consider capital X equal to capital N, which is the set of natural numbers. Now let us take any but specific, either it's 7 or it's 8, it has to be particular number from the set of natural numbers. So let us take any small x from the set of natural numbers. Now if I want to say x is greater than equal to x, this is true because x is actually equal to x. For any single number that I choose, small x is equal to small x, right? 7 is equal to 7, 3 is equal to 3. 14 is equal to 40. So x is equal to x. Naturally, x will always be greater than equal to x as well. So this is true for all value of x. So this is true for all value of x. This is the symbol for all x. So it's like an opposite, it's like reverse upside down A. It's basically, in the books you will find it like this. Clearly speaking, this is the symbol for all. When I'm writing it here, it becomes like this basically. But it's true for all values of x, right? You take whatever value of x you take, whatever natural number you take, it will be greater than equal to itself because it is equal to itself. It's just itself, right? So this property does hold. So what can I conclude? I can conclude that the property holds. So reflexivity holds for the, reflexivity holds for the given relation and set. So for the given relationship, that is greater than equal to, and for the given set, that is the set of natural numbers, reflexivity holds. This property is called the reflexivity property, and that is what I mean when I say that a relationship is reflexive. So that is, we say that the relationship is reflexive. So the relationship, or the relation itself, the relation is reflexive. So when I say that the relation is reflexive, I essentially mean whichever element I choose from